What's the atomic number of protons, you said, which indirectly tells us the number of electrons, because an atom always has to be electrically neutral in its native state. Okay, you told me how many electrons that the first shell can hold, how many every other shell can hold, so we have that pretty well. What does the atomic mass tell us? How do we calculate the atomic mass? We look at what? The proton and neutron numbers, and the proton and neutrons are found where in the atom? In the nucleus. Very good. Do all atoms have to have the same number of protons and neutrons? No. Right, because you look at hydrogen, right? Hydrogen, we know, has an atomic number of 1, meaning it has 1 proton, and that means it has 1 electron. But when you look at the atomic mass, it's only 1.00795. There's nothing else. There are no other particles. There's nothing else found in the nucleus, just that 1 proton. There are no neutrons. So that's why its atomic mass is 1. But a lot of atoms do tend to have the same number of protons and neutrons, but it's not a given. What happens if atoms of the same element have same number of protons and electrons, but they have different numbers of neutrons? What are they called? If an atom of the same element, for example, carbon. What did you say? Yes, an isotope. Huh. Well, it says dry erase. It says it right on here. So I'm going to try to use this. But I must admit, I'm a little nervous. This was a very high-tech looking dry erase marker, and I'm not very tech savvy. All right, so carbon, we mentioned, okay? Carbon 12, C12. The 12 is the mass. So carbon 12 has 6 protons, 6 neutrons, and of course 6 electrons because of the proton number. Positive and negative charges balance out. C13, carbon 13, the mass is 13 now, has how many protons? 6. Still 6. How many electrons? Has to be 6. Right, because proton and electron numbers have to be equal. But what about the neutron number?
7.
It's 13, so it has to be 7, right? So 7 neutrons. So these are the same element. These are the same atom or same element, right? They have the same number of protons and electrons, but different numbers of neutrons because they're isotopes of each other. C12 is a stable isotope. C13 is unstable and has a half-life, which means it degrades by half after so much time. Okay, so that's the isotope. Now, any questions so far about that part, about what we covered? Anything? Okay, so then we talked about chemical bonding. So what was the strongest type of chemical bond that we described? What was it?
Covalent.
What kind of covalent? What kind? What is, sorry to sound sarcastic. Yes, nonpolar covalent, exactly. Nonpolar covalent bonding. And so explain to me the relationship that, I guess, creates this bond. What's happening here with nonpolar covalent bonding? They share electrons and they share them equally, right? They very stable arrangement. Sometimes people, when they start studying, they get confused. They're thinking to themselves, well, I thought the proton and the electron number had to be equal, but now since the atom is bonding and it has all these new electrons, how is it? Remember, what I said about having the same number of protons and electrons only applies to an atom when it's alone. It's going to have a regular, charge to itself. But bonding, remember I told you, just like in relationships, it's all about completing that atom's outer shell, Okay, so with nonpolar covalent bonding, atoms are sharing electrons and they're sharing them completely equally. So usually this type of bonding happens between atoms that have the same ratio of electrons that they're sharing. Like we said, carbon is a great nonpolar covalent bonder because it has 4 electrons in its outer shell and it can have 4 more. That means it's going to share half of its electrons with whatever. Hydrogen's also great for that because it has an atomic number of 1. So it has 1 proton, 1 electron in its shell, and it can have 1 more because it's the first shell, right? So it too shares half of its electrons, and that's what makes those types of atoms good for nonpolar covalent bonding. Okay, the second strongest bond type that we talked about was what? Polar covalent bonding, right? Now, how is polar covalent bonding different? Okay, so you're still sharing electrons, but you're sharing them slightly unequally. Okay, so the example we gave, one that's really important for us, is water, because oxygen has an atomic number of 8, meaning how many electrons does it have in its outer shell? 6, right? So it only needs 2 more electrons. So it only is going to be sharing 1/4 of its electrons. But hydrogen, if it bonds to hydrogen, as we just mentioned before, hydrogen shares half of its electrons. So there's a very unequal sharing dynamic in terms of how much. So because of that, like we said in relationships, that sometimes when one component of that relationship is giving more than another, then the one that's receiving that sometimes expects more. Now, of course, that may not be healthy in human relationships, but it works really well for water, right? So what happens is we have, at certain moments, oxygen tugging on hydrogen's electron a little bit, and that will impart a slight negative charge on oxygen because oxygen still has 8 protons, but it's kind of taking on a little bit more of another electron, so it has a slight negative charge. Hydrogen, on the other hand, is losing that electron a little bit, so it has a slight positive charge. So this is good, these charges that are established. Why? Because it makes water a really good solvent, especially for things that are ionic, right? So we're going to talk about ionic bonding next. But what can water form around ionic compounds? Help them dissolve. Again, it depends on the orientation of the atom. Sometimes the hydrogens will face the sodium or chloride, yeah, whichever one. Sometimes the oxygen faces. But what are those circles called that water can form? Hydration spheres, right? Those form around ionic compounds. So ionic bonding now is a little weaker in terms of its bonding relationship because here we don't have any sharing of electrons. Here we have a complete give and a complete take of an electron, right? So that makes one of these atoms eventually positive and one of these atoms negative. So what is the positive atom called? Cation. And then negative one? The anion. Very good. And so if we're forming a hydration sphere around the anion, what orientation would water have? Would the hydrogens be facing the anion or the oxygen? Which one? Or hydrogen, right? Because the anion is negative, right? So the slight positive charges of the hydrogen are going to be orienting around that. Whereas the cation, which has the positive charge in the ionic compound, the slight negatively charged oxygen will face it. So the orientation will be slightly different because of that. So if we go back, you can see that The cation, again, positively charged, the oxygen atoms are going to slightly negatively charged, are going to surround the cation. Whereas the chloride, which is the anion, the slightly positively charged hydrogens are going to orient themselves around that. Make sense? Have any questions? Okay, and then the last type of bonding that we talked about, and this is where we're picking up today, is the hydrogen bond, which is very weak, but there actually is strength in numbers. But hydrogen bonds, they're very, very weak attractions between very slight charge differences. So it's always depicted with a dotted line. These bonds are easily broken and they can easily reform. But generally, this type of bonding happens between water molecules. Remember, the type of bonding that happens between atoms within a water molecule is polar covalent. But between neighboring water molecules, we have hydrogen bonding. So we have slight positive charge on the hydrogen, slightly attracted to the slight negative charge, bless you, of oxygen. Because of hydrogen bonding, water has many very special properties. Some of these properties are, for example, surface tension. Surface tension has basically two components, adhesion and cohesion. What happens with surface tension and how hydrogen bonding is related to this is water molecules have the ability to bind with other water molecules this way. And they can also bind with other polar surfaces. So polar is another word for hydrophilic, which we talked about on the previous slide. Things that are polar interact with water. They like water. They can, Non-polar is synonymous with hydrophobic. So non-polar things are things like waxes or oils that can't interact with the water. Now, surface tension, we can illustrate it. If we had a glass slide like we have upstairs in the lab, and we have one of those real thin cover slips, and we put a drop of water in between the glass slide and the cover slip, what's going to happen? Is going to what? I can't hear. That boiler just went off when you were trying to talk. What'd you say? Yeah, they get stuck together like a glue. Why is this? Because through hydrogen bonding, the water molecules are attracted to each other. Plus, through hydrogen bonding, the water molecules can attach to the glass surfaces as well because it's polar. So that's going to hold those two pieces together like a physiological glue, basically, which is very interesting. If you took two glass slides and you put water in between them, they're actually kind of hard to pull apart. But physiologically, this comes in handy for us because you know that there are serous membranes. We've talked about this. You guys talked about it in anatomy. Serous membranes are membranes which secrete water. Serous membranes, an example of this, are the parietal and visceral pleural membranes, right? So there's a visceral pleura that covers the surface of the lungs. You have a parietal pleura that covers the cavity, the wall of the pleural cavity. And both of those membranes secrete a thin layer of water. Just like those two glass slides together, those membranes are going to be held together. So the lungs are going to be held to the body wall. So when you inhale, the body wall expands, and when that happens, the parietal pleura pulls on the visceral pleura and opens up the lungs. And likewise, when you exhale, the visceral pleura pulls on the parietal pleura, and the lungs can then retract. If those membranes pull apart, the lungs would collapse. So that's where surface tension comes into play, and why hydrogen bonding is so important. Another property of water is it has a high heat of vaporization, which means that it's going to take a lot of heat in order to change water from a liquid into a gas, into steam, right? And that's good because when you think about it, a lot of our body is water. Our plasma of our blood is water. You know, again, our serous membranes